Hello, fellow antelopers. This is Thomas Chad Barton with my Grand Canyon University Chem 520 Analytical Chemistry final project for Dr. Dave Blank. And today we will be going over sodium azide, which has the ionic compound formation of sodium and 3 nitrogen molecules. So we'll go over this molecule. We'll have some facts. We will go over some historical uses, some modern day uses, and some of the effects that it's had on humanity. And we'll have some forward-looking thoughts on how we can improve upon this molecule or replace it. But why sodium azide? Well, it's heavily involved in many industries, as we will see. It has an expected year-over-year adjusted growth rate of 5% to $500 million worldwide. So it is ubiquitous. It was heavily involved in the 2022 Nobel Peace Prize in Chemistry. And as alluded to earlier, the environmental impact for the future is great. Okay, some quick facts. Sodium azide was first synthesized in 1892 by Johannes Wislicenus, and it is indeed man-made. Molecular weight is 65.01 grams per mole, and it is a colorless white crystalline solid at STP. Adding heat rapidly decomposes it into a solid sodium and nitrogen gas. And this property makes it great for industry. It has a trigonal planar geometry with dispersed double bonds, which allows for rapid and high-strength bond formation, which gives it some of its great industrial and predictable uses. And it is classified as a toxic poisonous substance by the CDC. That is because it can inhibit mitochondrial function, interferes with some of the enzymes, and it also will bind irreversibly to the heme unit, that is the iron unit in hemoglobin. Okay, some of the historical uses. As discussed earlier, if you add heat, it will rapidly and consistently decompose into a sodium solid and a nitrogen gas. This has made it great for use in airbags in your cars and rocket pressurization. If you want to move certain fuels from one point of the rocket into the combustion chamber, you can use this as a catalyst. Adding water or mild acid can create hydrozoic acid. And this is a highly caustic and explosive compound to use in detonators or controlled explosions. Just to give you an idea, it has a reaction rate of about 8,000 meters per second, and TNT is about 7,000 meters per second. So it is greater than TNT with explosive force. Additionally, it is used in analytical diagnostic chemistry. A Swedish company named Hemiq in the 1980s developed highly precise manufacturing qualities, and they decided to develop something called a microcuvette, which you can see in the middle photo there. And what they were able to do was combine this microcuvette with Beer's law, which is located over on the right picture there, and be able to come up with a concentration of hemoglobin. So developing the precise manufacturing techniques allowed them to hold the path length constant. They were able to do the molar absorptivity of the heme azide compound and select an absorbance, and that would give them the concentration. The wavelengths that they measured at are 570 and I believe 880 and they measure at 880 to account for the turbidity of blood. A lot of background interference in blood, so they measure at 880 to subtract that from the equation. Today, 4 HemoQ tests are performed each second worldwide, and it is mandatory for children to get hemoglobin tests done when they are young. I had the pleasure of working with them for about 8 years. Great company based in Helsingborg, Sweden. Skål. Now, moving on to modern day, a modern day use. So let's talk about the 2022 Nobel Peace Prize in Chemistry. It was awarded to Dr. Meldal, Dr. Sharpless, and Dr. Pertuzzi for their work in click chemistry. Click chemistry, very briefly and in a broad sense, is the development of a stable and predictable chemistry that can link different chemical compounds in a methodical manner, similar to the concepts of clicking Legos together, as you can see over there. This may seem like a simple concept, but is extremely valuable when it comes to building large molecules or molecules that are of use in the world today. So, a little bit more in depth on click chemistry, we are wanting to connect two different molecules, and the scientists discovered that using a molecule that is labeled with Azide, our little friend, and an alkyne labeled molecule, you would get a predictable outcome. But that only occurred, as they discovered, in the presence of copper. Copper would act as a catalyst for this reaction to give it reliability and predictability that they were looking for. So you mix an azide labeled molecule with an alkyne labeled molecule, and you will be able to link the two molecules. This worked for a lot of different molecules in different reaction conditions. Okay. However, there was one problem. The reaction was not viable in living organisms in concentrations that they needed for the stability of the reaction. So in stepped Dr. Pertuzzi, who developed a way of doing click chemistry, that can be done without copper inside living organisms. She went on to assist in the Nobel Peace Prize, but labeled her chemistry bioorthogonal chemistry. Here we have an azide labeled biomolecule with a cyclotine labeled probe. No copper needed, and we are able to get predictable, stable reactions out of this. Very, very valuable. Okay. So now we've seen that this chemical can be very valuable in the world. It can be used for many, many different processes. But at what cost? Sodium azide is classified as a toxic substance by the CDC and requires much care in how it's disposed of. You cannot simply throw this down the sink or in the trash. It can react within the pipes, especially lead pipes, in older facilities, and cause harm to the environment. To take a step back, we are now creating about 10 million man-made compounds per year. And conceptually, if you think of a man-made molecule, it's not decomposing at the STP rates that we need in the temperature and pressures in this world. So they can kind of build up in the world. If you think of plastic, plastic will be thrown into a dumpster and go to the dump, and it doesn't biodegrade based upon the natural world. This is similar to azide, and many of the 10 million man-made compounds that are made. So it's a little bit of a problem. Additionally, sodium azide was used in test kits that were delivered to U.S. homes during COVID pandemic. So if you think of the COVID pandemic as a race against time with man versus the virus, we had to lean back on using azide chemistry in order to get results that we needed. But this meant delivering toxic substances into the homes of millions of people in the U.S. So as you can see, it was a bit crude and non-elegant in how we solved that problem. So how will these new substances affect our Earth? What can we do about it? So there's a common term in military history called fighting fire with fire. So essentially we are developing these new compounds, these man-made compounds at rates unheard of before in the history of mankind, giving our computing power. So we will have to use computing power to get us out of this mess. And because there will be breakthroughs in artificial intelligence and quantum computers, this will allow us to replace toxic compounds like sodium azide with nature-friendly compounds. So as we move through and develop more and more materials and material science, we can take some of these older archaic toxic substances and find equal replacements so that we can dispose of them and get rid of them in a timely manner that will recycle back into our Earth safely. So we will be balancing technological and social needs with our environmental needs. So that's it. I hope you enjoyed this unknown but mighty compound, something that's been a part of my life for many years with the HemeQ hemoglobin tests. And I really look forward to, I'm happy that you guys have learned about this product. That's it for me. Take care and have a wonderful semester.